This lecture is an introduction to the magnetic field, which is a new concept in this second semester physics course. We'll talk later in the semester how the magnetic field relates to the electric field, and all of that together is called electromagnetism. But today we'll mostly just talk about the magnetic force, and that's a force of the magnetic field on a moving charge. Together with the electric force, which you remember is just QE when you have an electric field, they form a force called the Lorentz force, which is the connection between electricity and magnetism and Newton's second law. So you can do mechanics with magnetic and electric fields. We'll first talk about an overview of magnets and magnetism in general, very briefly. And then we'll talk about how you probe the magnetic field with something called a compass. We'll talk about the vector product, which is also called the cross product, something that you might remember from first semester when we talked about torques. It's necessary here because the magnetic force on a moving charge involves that vector product. And so we'll talk about what that magnetic force is, and then we'll do three examples. One, just a simple calculation of magnetic force for a given velocity and magnetic field. We'll talk about something called a velocity selector, and finally the trajectory of a charge as it moves in a uniform magnetic field. So first a bit about magnets and magnetism. Magnets were found originally just as rocks on the Earth, and it turned out that these rocks were somehow attracted to each other. So you might have one rock and another rock, and you would find that this rock would be attracted to the other rock. And it turned out that if you do some experiments, you see that you could arrange these rocks in a different way such that the second rock would be repulsed by the first rock. So maybe there's a force away from it. And the way that you can explain that is you can say, well, each of these have what's called a pole, two poles, like a north and a south pole. And if you put opposite poles next to each other, then they're attractive. And if you put same poles next to each other, then they're repulsive. And I'm sure you've observed this with your refrigerator magnets. But the key here is that a magnet is an object that has two poles. And even if you take one of these rocks and you break it apart, so let's take this little rock and we'll break it apart so its north pole is over here and its south pole is over here. It turns out that you'll find a south pole and a north pole right where they were broken. So the magnet lives on, and it also will still have that dipolar feature. It will have two poles to it. And of course these two magnets here would attract each other, sort of put them back together again. So those are forces between magnets, and that was just sort of an observation that was made. Magnetism, so the sort of is the reason that rocks have are magnets, or that have magnetic fields. It's a complicated discussion, and we're not really going to talk much about it here. You can take a look in your textbook about it. But the underlying feature is, we'll talk in a week or so about how magnetic fields are generated by moving charge. In particular, if you have a current, then a current in a wire will create a magnetic field. And if you just have a moving charge, that itself will create a magnetic field. So the origin of magnetism comes about because you have atoms, which have a positively charged nucleus, and then they have a negatively charged electron, and that electron sort of spins around the nucleus, and it can create a magnetic field. So that's one way that you can create magnetism. It turns out that the more the more important way that a atom can create magnetism is because the electron itself has what's called an intrinsic spin to it. And so there's sort of, we can just draw like a little spin vector which creates its own magnetic field. And what we really mean by this is that there's like a north and a south pole to the electron itself. So it turns out that magnetism, the strongest magnetic fields that you find in these rocks are called ferromagnets. And those are rocks that have a lot of iron in them. And iron has a lot of unpaired electrons in their outer valence shell. And those unpaired electrons are each little magnets. And then those little magnets can align with each other and give that rock some larger magnetic field. So, so this is a very brief and mostly wrong description of how magnetism comes about, but it originates from an atomic or a quantum phenomenon, which then appears within that material that you have. So just to say a couple words about it, there's something called ferromagnetism, which are sort of the strongest magnetic fields that you'll find in rocks. And ferro comes from iron. So iron is one of the best elements to create that, and that's because of the unpaired electrons in its valence shell. There's something called paramagnetism, which is the ability of a material to get a magnetic field in it when it is exposed to an external magnetic field. So ferromagnetism will have a permanent magnetic field, whereas paramagnetism can get a temporary and both of those are when they're exposed to some external magnetic field. And then finally there's something called diamagnetism, which is that if you expose if you expose to an external magnetic field, it gets an oppositely directed magnetic field. So each of those things are things that you can look at in your textbook, and we're not going to focus much on them anymore, except it's good to know that that's sort of where the magnetism comes from that we observe in the natural world. What we will talk about is the generation of magnetic fields by current, and that will be a topic of a later lecture. So I've already been using the word magnetic field, but we should sort of talk about what that means. So we talked about how there are rocks with two poles, and the sort of canonical magnet that we might draw is called a bar magnet, and we draw the north and the south pole of that thing like this. We talked about how you have an attraction of a south pole to a north pole. So if I were to take another little magnet like this, then there would be a force of attraction on that other little magnet because the poles are opposite next to each other. Another way that you can think about that is that this second magnet will align itself with the first magnet. And that alignment, we say, is an alignment with the magnetic field of the first magnet. Now, a compass is just a small magnet that is allowed to rotate so that you can check that alignment. So if we were going to look at a bar magnet, we could probe its magnetic field by placing a compass in different positions around the magnet. So let's say a compass looks like this, and we'll just draw a compass needle like this, where the pointy end is the north and the wide end is the south. So if we're going to probe the magnetic field near a bar magnet, it's going to look something like this, because the south end will align with the north end. And then down below, it'll look something like this, because the north will be attracted to the south. And then if you sort of put it off to the side, again, you'll get the north attracted to the south, the north attracted to the south, something like this. And off to the side here, the south attracted to the north, and the south attracted to the north. And you can start to see what the magnetic field looks like, because we say that each of these compasses will be aligned with the magnetic field vector at that point. So we could draw the magnetic field vectors. They sort of look like this. So these are the magnetic field vectors of the bar magnet as probed by the compass. If you put a compass over here, it'll turn out that the compass actually looks like this. So the magnetic field off to the side would look like that. So let's look at that as a whole. What does that mean the field of a bar magnet looks like? We have north, south, and if you just sort of look at what we have, you can see there are field lines that are going into the South Pole and out of the North Pole. And then what happens is they actually wrap around. So the field lines are closed. So we get these closed looping field lines. And in fact, because of that idea that if you break a magnet, you never get just a single pole, you always get a dipole, these field lines, they actually go through the magnet like this. So this is what the field of a bar magnet looks like. So we can put a few more arrows to show what it looks like. And that will be the field of a bar magnet. So every sort of magnet that we create, whether it's a bar magnet that's just created by rocks from Earth, or whether it's a magnet, so-called electromagnet, that's created by current, all of these magnets can be made to look sort of like a bar magnet, and it'll be useful to see what's the north and the south pole of that magnet. So one particular magnet is the Earth. It turns out that the Earth has a magnetic field, and you may know that if you hold a compass in your hand, that compass will align itself with the Earth's magnetic field, and the compass needle, the point of it, which is the north of the compass needle's magnet, will point to the geographic north direction on Earth. So let's just show what that means. So if you're standing sort of in Grand Rapids, next to the Blue Bridge maybe. So here's the Blue Bridge. The river goes underneath here, and the river flows from north to south. So this is the north direction in Grand Rapids. If you're standing there with your compass, you will see that the compass needle points to the north. So the compass needle points to the north, which means that at least in the horizontal direction, the horizontal component, there's a magnetic field in Grand Rapids that points to the north, like that. It turns out that that's actually the weaker part of the magnetic field. So if you take your compass like that, then you could align a different kind of compass, which we could call a vertical compass, sort of like a Ferris wheel. So allow a compass needle to then rotate with the magnetic field, but align it along the north-south direction, then it will turn out, and I guess I should try and draw that a little bit better in perspective. So we're going to align it in the north-south direction. So this is the north-south direction here. It turns out that the compass needle will actually point down mostly. So the magnetic field line points up the surface of the Earth in the north direction, but if you actually look at what the field line is doing by allowing the compass needle to rotate in the vertical plane, you'll see that the field line actually points down. So at this position in Grand Rapids, the magnetic field points down into the Earth like that, with a little bit of a tilt toward the north direction. So what does that imply about the magnetic field of the Earth? Well, let's draw it. So here's our Earth. And we can draw like Alaska and the United States, South America like this, maybe Australia's over here, Japan, Russia, etc. And I drew it like this because what I wanted to do was put Grand Rapids right on the limb of the sphere here. Because what we did was we just found out what the field line of the Earth looks like at that point. And what we said is that it points mostly into the Earth and partly north. So if this is like the normal to the Earth, the field at that point looks like this. Mostly into the Earth, partly north, like that. Okay, well, Grand Rapids isn't special, so one should imagine that if you looked sort of over on the other side, over in China, the magnetic field would look sort of the same. So it would be, you know, mostly into the Earth and partly north. So that field line might look like this. And then down below in the southern hemisphere, it probably looks sort of symmetric. So it's going to be it's going to be sort of mostly out of the Earth and a little bit to the north, like that. And then mostly out of the Earth and a little bit to the north, like that. So what does that mean? Well, it means that the field will look like this. Coming into the North Pole, meaning the place where Santa Claus lives, and coming out of the South Pole. So the field lines that we have from Grand Rapids look like that. The rest of the field lines look like this. And we see that, oops, I drew that wrong, didn't I? We said that it's going into the North Pole and out of the South Pole. So this is what the magnetic field of the Earth looks like. And then, of course, the lines will continue through the Earth. So what does that mean? Well, as we saw from the bar magnet, magnetic field is defined to go into the South Pole and out of the North Pole of the bar magnet. So if you're to draw a bar magnet here on the Earth, do it in black, then this must be the North Magnetic Pole, and this must be the South Magnetic Pole. So there's a bar magnet inside the Earth, but it's upside down relative to the directions of the Earth. And we see that just because of the way that a compass points here. And it's just a naming convention, really, that the compass was named so that its North Pole points in the north direction. But if you follow that logic through based on what the field lines are doing, then that must mean that it's being attracted to the South Pole up in our geographic north. So that's what the magnetic field of the Earth looks like. Now, before we go on to talk about the force of a magnetic field on a moving charge, we need to talk a little bit about the mathematics of vectors, in particular something called the cross product or the vector product. So you remember there's something called the scalar product, which takes two vectors and gives you back a number, or a scalar. The vector product is a product that takes two vectors and gives you back a vector. So we write it as like this, A cross B. And that should give you back some C vector. So what is that? Well, it's a vector, so that means that we need to indicate both its magnitude and its direction. So let's first talk about the magnitude. And the magnitude, it turns out, is something that looks similar to the expression for the dot product, for the scalar product. It's the magnitude of the first vector times the magnitude of the second vector times the sine of the angle between the two vectors. So if we had like a vector A that looks like this maybe, and a vector B that looks like this, then the angle that we're talking about here is the angle when you put their tails together. So that would be like, here's A, and here's B, and this angle is what we're talking about. This is theta A, B. This is the A vector and the B vector. So you have to put their tails together to find out that angle in order to figure out what the magnitude of the cross product is. And because this is sine, you can see that if the angle between them is 0, meaning that they're parallel, then you would get a 0 here. So the magnitude of the cross product between parallel vectors is 0, and the maximum value that you get is when sine is equal to 1, so that's for an angle of 90 degrees. So when you have perpendicular vectors, you get the maximum cross product. Parallel vectors, you get a 0 cross product magnitude. But that's just the magnitude. That's not the whole vector. So we also need to know what the direction of it is. And the direction, you should think about it in sort of two parts. So the direction of C is perpendicular to both A and B. And a better way of saying that is that it's perpendicular to the plane of A and B. I don't mean to say minus there. I just mean the plane made by A and B. So a plane made by A and B, well, in this example here, A and B both lie in the plane of the page. If you put their tails together, you can sort of see that plane. It spans this entire flat page here. So you would say that A and B make a plane, which is the page. Now, direction of C is perpendicular to both of them. So that means that C must be pointing either out of the page or into the page. And to decide which one that is, you use the right-hand rule. So you use the right-hand rule to figure out which way. So you start out by saying, okay, I know that the direction must be perpendicular to both, so C must be perpendicular to the page, and then you use the right-hand rule to figure out which one it is, whether it's out of the page or into the page. So what is the right-hand rule? Well, the right-hand rule is you put your fingers along the first vector, and then you close your fingers in the direction of the second vector. You can't see my hand here, so I'll try and draw my right hand. So here's my thumb, and here's my hand there. So there's my thumbnail and the nails of my right hand. So I'm putting my fingers in the direction of A. You see that? And then I twist my wrist around, so do it with your hand, so that I can close my fingers in the direction of B. So if I want to do that, then my hand sort of gets to be at an angle here, and my thumb is pointing now into the page. And then I close my fingers in the direction of B. So then you sort of close your fingers in the direction of B. So here's my fingernails, and I'm closing. It's a terrible drawing, it's hard to see, but the idea is that you want to put your fingers in the direction of the first vector, and then close them in the direction of the second vector. And then your thumb, which as you can see in this picture, it's very, very clear, your thumb is pointing into the page, which is the direction of C in this particular example. So that's what you need to know basically about the right-hand rule. Let's take a look at a couple examples for the unit vectors, because sometimes it's easy to make calculations with the unit vectors. So remember, unit vectors point along the directions of of the Cartesian coordinates. So if we have x, y, and z, the I hat vector points along the x direction, the j hat vector points along the y direction, and the k hat vector points along the z direction. So what are the cross product of those vectors? Well, first let's try them with themselves. So what is, for example, I hat cross I hat? Well, as we saw from magnitude, if the vectors are parallel, which of course I hat with itself is parallel, then you get a 0 magnitude. So that's going to be equal to 0. And that will be true for, j hat, and for k hat cross k hat. So all of those will be 0. Let's try out a couple more. What is I hat cross j hat? Well, for this we use the right-hand rule. The magnitude will be 1 because I hat and j hat are 90 degrees apart, and their magnitudes are both 1, so all three of those numbers will be 1. But the direction you find by the right-hand rule. So put your fingers, your right hand fingers in the direction of x, so you're putting your fingers to the right of the page. Then I need to twist my wrist so that sort of the plane of my hand is perpendicular to the page, and I can close my fingers so that they go up the page, and then my thumb will point out of the page, which is the k hat direction. So I hat cross k hat is equal, I hat cross j hat is equal to k. Let's try one more. How about I hat cross k hat? Well, put your fingers in the direction of the x-axis. So the fingers of your right hand to the right across the page. Now I want to close my fingers in the direction of k hat, so that means I need to twist my wrist all the way around, sort of dislocate my shoulder so that I can close my fingers out of the page. I close my fingers out of the page, and then my thumb will be pointing down the page if I do that. And so that means that it's the negative j hat direction that we get for that. So you'll have to practice that in person, but that's the basic idea of how to deal with the vector product. So now we can use that in our theory of magnetic forces. So we've already talked about the fact that there's something called the magnetic field. We talked about the fact that there are field lines, and there is also a magnitude of the magnetic field, so field strength. And we represent all of that with the variable B. And then if you have a moving charge, so a moving charge Q with velocity V experiences a force, which we call FB, when in a magnetic field B. So let's draw this. So if we have a charge, Q, and it has a velocity V, then we might have a magnetic field. I guess I'll draw it with B, and it will experience a force. So if the charge is moving, it experiences a force. And what is that force? Well, it's a vector, so we have to write it as the vector equation, and it turns out to be the charge, which could be positive or negative, times the velocity vector, crossed with the magnetic field vector. So you can immediately sort of see what the direction of the force will be. Remember, the direction of V cross B will be perpendicular to both of them, or a better way to say it is perpendicular to the plane made by the two. And in the drawing that I've made here, both V and B are in the plane of the page, which means that the plane is the page, which means that the result should be either out or in to the page. So let's find V cross B here with our right-hand rule. Well, V cross B, if we put our fingers sort of up in the 2 o'clock direction across the page, Then we need to twist our wrist so that our fingers can close into the 4 o'clock direction, and then your thumb should be pointing into the page. So the force in this example here, I'll draw it, will be into the page. And I'm drawing it with, so it's hard to draw a three-dimensional vector here, or to draw vectors in the third dimension, but the way that we do it is we express the vector as into the page with an X like this, and as out of the page with a dot. And so let me tell you why that is, so or what the logic is behind that. The idea is that you think about a vector as being a rocket, or maybe an arrow. I guess I'll draw an arrow here, sort of a cross between a rocket and an arrow. And so if you look at this arrow as it's coming towards you, you'll see just the tip. And if you look at the arrow as it goes away from you, you'll see those fins, or the feathers of the arrow in the back. So this is how we draw a vector that points into or out of the page. So what we've done here is we've said that the force is pointing into the page, and that's because V cross B is in that direction. Now I should have been a little bit more careful. I didn't tell you what the Q was. And you can see that V cross B will give you some vector in some direction, but that vector could be changed by the Q because the Q could be negative. So I should have said here that Q is positive, and that means that when you find V cross B, that direction, which we found to be into the page, will be multiplied by a positive number, so force is also into the page. If Q is negative, though, you'll have to flip it. So that's the basic idea of the magnetic force on a moving charge. And it just turns out, based on the units of these things, that will all be in newtons. The units of magnetic field in the SI units are called Tesla. Tesla was a famous Yugoslav physicist who came and lived in America. He worked with Edison, and in fact got in a huge fight with Edison. And Tesla actually gave us basically AC power, which is how we generate and transmit power across the world, basically. So Tesla is an important historical figure. So the magnetic field is in units of Tesla, and just from that equation you can see that a Tesla, well, we have newtons is equal to coulombs times meters per second times Tesla. So I guess that a Tesla is equal to a Newton over Coulomb meters per second, turns out. Just using this equation here to figure out what the units are. Before we move on and do some examples, we should mention that you don't have to just think about a single charge moving through a magnetic field, but instead you can talk about a current carrying wire. So this is our equation for the force due to a charge moving in a magnetic field. But if you re-express the charge and the velocity in terms of, say, the drift velocity of a charge moving through a wire, then you can write this in terms of current. And let's do that. So a wire with current I experiences a force, and that force is also called FB, and we write it as current I, L vector cross B vector. So L vector is in units of meters, and it's a vector that points along the wire. So if I have a wire here, which has a current flowing in it, remember the current is the direction of positive charge carriers, and then the length of that wire is the length L, but the vector L has magnitude L, but it points in the direction of current. So this is the vector L. And then if all of that is within some magnetic field, then that wire will experience a force, and I think I drew it exactly the same way as above. That force will be also, take your right hand rule along, fingers along L, close towards B, this is B, and your force points into the page. That's our FB force. I don't think we'll do any examples with that today, but we'll certainly see that in the future, that a current carrying wire also experiences a force, exactly because a current carrying wire has charge moving. And if that's in a magnetic field, then you get a force on those charges. Our first example is just a straight calculation. So we have a particle of a certain charge, minus 20 nanocoulombs. It's moving with a certain velocity, which is given in terms of its x and y direction. And we're asked what is the force on the particle in a particular magnetic field in some direction. So we're given these unit vectors that tell us the x and the y directions, so we should probably draw ourselves a xy coordinate system. And then let's just sketch out a picture. So the v has one component in the positive x direction, 4 times 10 to the 4th, and then a y component in the negative y direction, which is slightly larger. So it looks like we have like vx looks like that, and vy looks like that. So the v vector is something like this. And then we're told that the magnetic field points in the I hat direction. So we could draw just a single magnetic field vector, and then we could draw magnetic field lines. So maybe we'll draw them in green again. So there's a magnetic field that points in the positive x direction. And just like we did with electric fields, we treat the magnetic field lines as uniform if they have equal spacing there. So if I'm talking about a uniform magnetic field, which is what this means, it says it's a single value at any point in space, then I draw magnetic field lines that are equally spaced. So we have a magnetic field that points to the right, we have a velocity that points down and to the right, and then we have a charge which is negative. And so we could qualitatively look at this. Well, V cross B, put your fingers along V, so your fingers of your right hand go down at like 5 o'clock down the page, and then you want to close your fingers up to 3 o'clock. So if you need to, twist your wrist, but then close your fingers, and V cross B should be then out of the page with your thumb. However, remember our equation. Our equation is FB is equal to Q V cross B. And in this case, we find that V cross B is out of the page, but because Q is negative, this should be into the page. So it should be that we find something that is in the into the page direction, which I guess is the negative k hat direction. So let's calculate it directly. So we have FB is equal to Q times V, which I'll just write as, let's just write it as A I hat minus B J hat, so I don't have to write out those numbers. And then we cross that together with the B direction, and the B direction is magnitude B I hat. So I'm treating A as 4 times 10 to the 4th meters per second, B as 5 times 10 to the 4th meters per second. And so what do I get? Well, you just distribute the cross product here. So we get Q times, and then we have AB, capital B, I hat cross I hat. Maybe I should do this with square brackets and parentheses. And then you get minus BB, and we have J hat cross I hat. So what does that turn out to be? Well, this thing is I hat cross I hat, that's 0, because we found that the magnitude of two vectors that point in the same direction is 0. So we get a 0 there. And then we get minus BB, J cross I. Well, remember last time or in the previous page, we found I cross J was K. So this will probably be minus K, but let's check it. So if we put our fingers along the Y direction, meaning fingers up the page based on my coordinate system, and then you twist your wrist so that you can close your fingers to the X direction, then your thumb will point into the page. And so it indeed points into the page, which based on a standard X, Y, Z coordinate system is in the negative Z direction. So we write that as minus K hat. Okay. So what do we find? Well, the minuses cancel out and we get Q, B, B, K hat. But of course Q is negative, so we're going to get it something in the negative K direction, and we can just calculate what that number is. So it's minus 20 times 10 to the minus 9 coulombs. And then little b we found was 5 times 10 to the 4th. And big B we had was 2.4 Tesla. And that will come out to be some number. Oops, I left out the K hat. So it's going to be some number, some positive number, times minus K hat. And I'm not going to calculate it right now because I don't have a calculator. But that's the basic idea. And notice that that agrees with what we found when we were thinking about it qualitatively, that it should be into the page based on our right-hand rule. It also works out quantitatively when you take these cross products of the unit vectors that appear in there. Next question. We have a beam of protons that are exiting a particle accelerator, so there's something that speeds them up to high speeds. But there's a bunch of different speeds in this beam. So the question is, how do you construct what's called a velocity selector that will only isolate protons with a certain specific speed, which we'll call v naught. So this is an interesting thing that you can do with electric and magnetic fields. So let's think about the electric fields first. So if we have a particle, so this is just a proton, so it has a charge of the elementary charge, and that particle is incoming with some speed, v, and a velocity vector that's directed across the page. We construct this with a uniform electric field. So let's first make a uniform electric field just with parallel plates. So you can imagine building that in a laboratory. So parallel plates are sort of oppositely charged, and that will create a uniform electric field which goes from the positive to the negative plate. And now we can imagine what happens when that particle enters. It feels an electric force. So remember what the electric force is. Fe vector is equal to QE. So Q is a positive number in this case because we have protons, and E is a vector that points down, so that means that the force should be pointing down. So the force on this charge as it enters the uniform electric field will be directed down. And if we were to just allow it to go through here, you can see that it would sort of curve downward, just like exactly like a projectile motion problem, basically. And it might even hit the plate. It certainly could not go straight through because it has a single force on it. So the idea here is to try and allow it to go straight through. What I want is for the trajectory to go like this. And if that's true, then that means that the velocity vector is not changed, which means that I need to have a zero acceleration. And in order to have a zero acceleration, by Newton's second law, I must have that the sum of the forces equals 0. So I must have a force that balances it out that points upward. So what is that? Well, this is the magnetic forces lecture, so it must be a magnetic force. So there should be a magnetic force. Let's just put a question mark. So how do we get a magnetic force that points upward? Well, remember, FB is equal to QV cross B. So if I can construct a magnetic field such that V cross B points up, remember Q is positive, so it wouldn't change the force direction. So if V cross B is up, then I can do that. So let's try and see what it is. Well, let's just guess. So maybe it's a magnetic field that points up the page. So if I had a magnetic field that pointed up the page, then V cross B, take your right hand, your fingers go along the V vector to the right, to like 3 o'clock. Twist your wrist so that you can bend your fingers up the page, and your thumb would be pointing out of the page. So that would be wrong, because that would give us a force that's out of the page, and then the particle would not be balanced in that way. It would accelerate in some direction. So that's not right. So we don't want a field that points up the page. What about a field that points into the page? Well, then we have V to the right, and then close your fingers down into the page, and your thumb then points up the page, and that's exactly what we want. So it turns out that the magnetic field that will work in this situation is a field that points into the page, and it should really be everywhere. So it's a uniform magnetic field that points into the page. And let's just check ourselves again. V to the right, 3 o'clock with your right hand. You should be able to just close your right hand into the page then, and your thumb is pointing up the page. So that will be the force that we want. So that's the first part of the question. How do we construct it? Well, we construct it by making a magnetic field, a uniform magnetic field that points into the page. Now we need to know what the particular strength of that magnetic field is. And we do that by looking at this free body diagram. So the free body diagram has the magnetic force pointing up. It has the electric force pointing down. And we've assumed a zero acceleration. So looking at Newton's second law, the net force on the particle is equal to mass times acceleration. The net force in this case is the magnetic force plus the electric force. And we assume that the acceleration is equal to 0. So this equation tells us that the magnetic force must be exactly opposite to the electric force. But in magnitudes, if you just take the magnitude of both sides, then that means magnitude FB is equal to magnitude FE. So what are those things? Well, we have the equation for FE up here. So magnitude FE is just equal to absolute value Q times magnitude E. And magnitude FB, we found that in the very beginning when we were talking about, or did we find, maybe we didn't. So let's do it now. So magnitude FB is equal to, well, we'll have absolute value Q, and then we have magnitude of V cross B. So we found that when we talked about the mathematical expression, what is the magnitude of a cross product? So it's going to be equal to magnitude V, magnitude B, sine of the angle between V and B. So in this case, well, what do we have? We have V pointing across the page, we have B into the page, so those two things are perpendicular. So our sine will just become 1 because our angle is 90 degrees. And our magnitude FB is just absolute value Q, speed V, magnitude B. So if we want to select out a particular velocity, we can rearrange this equation. We must have, if we choose, let's say that we were given an electric field, so we were given some apparatus that creates an electric field, then we must create a magnetic field which is going to be equal to E over V. So given some uniform electric field, E must use B is equal to E over V to isolate, well, let's call it V naught now, particles with speed V naught. And what do we mean by isolate? Well, let's draw a little picture of it. So here's our positive plate and our negative plate. Here's our electric field coming down. Here's our magnetic field going into the page. We send in a particle with a V greater than V naught, and it will experience more magnetic force than we want, and so it will sort of hit this plate. You send in a particle with a speed equal to V naught, and that will experience exactly the free body diagram that we asked for, which means that it has an acceleration of 0. And if you have, oh, I drew this wrong, didn't I? So I wanted this to be a larger one. So that's greater than V naught. And then if we have a smaller than V naught vector, then that means that the magnetic force here will be smaller than the electric force, and therefore the electric force will dominate, and therefore the trajectory will look like this. The electric force will pull it into there. So you can see that the only things that arrive on the other side are those particles that come out with a V naught. So we've isolated the particles of a certain speed. And you do it by arranging the magnitudes of your electric and magnetic fields. Last example, we have an electron that moves with a certain velocity, we're told in the x direction, and it passes the origin from the negative x direction, entering a large region of uniform magnetic field, which is given as 5 times 10 to the minus 5 Tesla. That is approximately the magnetic field of the Earth. And let's say that that magnetic field region spans sort of a 2 meter by 4 meter by 4 meter region. So let's sketch this out. The question is, where and when does the electron exit the B field? So it's probably sort of ridiculous to imagine that one could create a magnetic field that looks like this, but we'll just go along with that. So we have a particle. We're told that it's an electron, and it comes in with a certain velocity. It's moving in the positive x direction. So here's its v. It has a q, which is less than 0, a negative q, which is minus e, and it has a mass. The mass of an electron is 9 times 10 to the minus 31, is that right? Kilograms. E, remember, is 1.6 times 10 to the minus 19. We'll use those at some point. And then it enters a region of magnetic field. So we're told that there's a magnetic field sort of in this region here. And we're told that the magnetic field points in the k hat direction. So k hat would be, if this is x and y, k hat is out of the page. So we'll draw a magnetic field that points out of the page. So the particle enters that region, and then at some point it exits. And the question is where and when. So how do we do that? Well, we need to do a little bit of qualitative analysis to see what's going on here. So let's imagine that the particle has just entered the field. I'll erase the magnetic field vector there. So it has some velocity vector pointing to the right, and it's within a magnetic field that points out of the page. So here's our V, and our B is pointing out of the page. So let's determine what's the force on the electron. So remember, FB is equal to QV cross B. So let's first find V cross B, and then because the electron is negative, the force will be in the opposite direction. So V cross B, take your fingers of your right hand. I hope you're doing this with me. You put your fingers to the right in the positive x direction, and then you need to close your fingers out of the page. So for me, I need to twist my wrist around so that my palm is up, and then I close my fingers out of the page, and I find that my thumb points down the page. So V cross B, the vector V cross B, will point down the page, but because Q is negative, it means the force will point up the page. So we can draw the force, the magnetic force, as pointing up the page. So the moment the electron enters the field, it feels a force that points up. And you notice that force is perpendicular to the velocity. So what that means is that it will not change the speed of the electron. It will only change the direction. And it will change the direction in such a way that maybe in some later moment, it's going to be looking like this, and it will have a slightly different direction. However, it will have exactly the same magnitude. Okay, so if it's there, then what will happen to it? Well, then it will experience a force, and it will be FB is equal to Q times V cross B. So put your fingers along the V vector, sort of in the 2 o'clock direction. Twist your wrist so that you can close your fingers out of the page with the B vector. And you see that that points sort of down in the 4 o'clock direction, but again, negative charge, so it'll point in the 10 o'clock direction. So we have a force which points like that. And because the magnitude was the same, and the velocity and B are still perpendicular to each other, these forces also have the same magnitudes. So the forces will be the same as it goes along. And you can already start to see what's going to happen here. It's going to come in, and it's going to curve exactly as a circle. This is circular motion. You have it's in fact uniform circular motion because your V is constant and your force is constant there. So you're going to get some circular motion. So the question was, where and when does the electron exit the B field? Well, we just have to figure out what is the circle that this particle is traveling on, and what is the radius of the circle. And then we could draw it. Maybe it's going to look like this, maybe it's going to look like this, maybe it's going to look like this, something like that. But we should be able to figure out where it will enter and exit, because it will complete one part of a circle. So let's do that. So the first thing we should do is figure out how these things are related, and we'll do that with Newton's second law. So taking one of these as our free body diagram, let's take the second one. So here's our charge with its mass. It has a B force that looks like this. It's going to be moving in the with a velocity in this direction. That's not really part of our free body diagram. But we should also indicate the acceleration of this thing, which will also be inward on the path like that. Now we write down Newton's second law. It's a very simple Newton's second law because the net force is simply the magnetic force. And then because we're dealing with circular motion, we usually choose a special coordinate system which points radially. So you can see that the radial direction is outward on the circle. And so I'm going to choose a coordinate system. Usually you call the direction that's along the velocity the tangential direction, and the direction that is outward to be the radial direction. So if I choose that special coordinate system, then I see that, well, first let's just write down Newton's second law in that coordinate system. So it's FB sub r is equal to MAR. What I see is that the R component of the magnetic force is going to be negative because it points in the negative radial direction, and AR will also be negative. And the reason I choose this is because I have an expression exactly for what AR is. That's just a kinematic relationship, and we know that that's equal to minus v squared over the radius of the circle that it takes. So there's going to be some, I don't know where to draw the radius, so I'm not going to draw it. Well, I'll just draw it here. So there's some radius to the circle here. It's starting to get to be an ugly picture. So AR, the R component of the acceleration, is negative. FBR is also negative, so I can write that as minus magnitude FB. The negatives will cancel out, and the magnitude of FB is going to be Q with an absolute value, speed, absolute value of V, B, magnitude of B, and sine of the angle between V and B. Remember, that's how we find our magnitude of the cross product. And that will be equal to mv squared over r. Again, the v and the b are perpendicular because v is in the plane of the page. Wherever it is, it's in the plane of the page, and b is out of the page. It's coming out of the page. So that will be 90 degrees angle VB, and this sine will just go to 1. So we're left with absolute value QVB is equal to mv squared over r. And now we can sort of arrange that a little bit. So we can cancel out one of the v's, and we get absolute value QB is equal to mv over r. Okay, so let's see. So what do we get from that? Well, one thing that we can derive is the r value. So the r value is going to be equal to mv over qv. And let's just type that number in. So let me type it into my computer. So m is 9 times 10 to the minus 31. Q is 1.6 times 10 to the minus 19. V is, remember, 2 times 10 to the 6. And B is 5 times 10 to the minus 5. So if I write mv over qb, I find that it's equal to 0.225, and that's in SI units because I put everything else in SI units, meters. So that's 22 centimeters. So the radius of my circle is 22 centimeters. What's the circumference of my circle? Well, it's 2 pi r. And so that is about 6 times 22 centimeters. So that's about 1.41 meters. The circumference would be all the way around, but you can see from this picture, it's definitely not going to go all the way around because this was 2 meters here. So in fact, it's going to go halfway around, and it's going to exit up here somewhere. So it's going to exit after going a distance of 0.7 meters, which means that it's going to exit exactly at the 2r point. So here's our box. The particle comes in here. It's going to go like this, and it's going to exit exactly 2r away from where it came in. So it's going to exit at y is equal to 44 centimeters, x is equal to 0, and z is equal to 0 because we assumed it was at the origin in the xy plane. Okay, so we found out where it's going to exit. Now, when is it going to exit? Well, we know its speed, and we know that the speed must be we know that the speed is constant, so the speed could be written as the circumference, 2 pi r, over the amount of time that it takes to go around the entire circle, which we call the period. So if it were to go around a whole loop, we could call that the period. Let me just say that. Period time for one loop. So I can eliminate v in terms of the period, and I can figure out the amount of time it takes to go around once. So let's do that. So I can replace this. I have r is equal to m times 2 pi r over t all over qb. Okay, and if I want to find t, then that's going to be t is equal to 2 pi r times m over q b r. And it looks like the r will cancel out, and so I just get whatever this expression is. So let's plug that in. So we have 2 pi m over q b r. Well, I find 3.14 times how much? 1, 2, 3, 4, 5, 6. So it's microseconds. Oops, that shouldn't be so big. Microseconds. 3.4 times 10 to the minus 6 seconds. So the electron will come in, loop around in a circle, and it'll exit not at t, exits at t over 2, which is, I guess, 1.5 microseconds, because it only completes a half circular loop there. Okay, that's